All right, so let's see if we can graph the quadratic function p of x is x squared minus 6x plus 8. And then maybe like sort out where the vertex is or something. So how do I start this? Good. Okay, we need to, or we could at least start by finding x-intercepts. Okay, do you guys want to do that?
Yeah.
Okay, so
X minus 2 and x minus 4.
good. So you guys notice that you can factor this into x minus 2 times x minus 4. Okay. So the x-intercepts are positive 2 and positive 4. Is that enough to give me a picture?
Kind of, not really.
No, you need to. Yeah, you need to.
Yeah, so far I have 2 pieces of information, and for a quadratic,
You know it's positive.
you really
it's
need
going
3. Good, I know it's pointed up at least, so that eliminates half of my issues, but I still have lots.
Intercepts the y-axis at 80? No.
Good, a y-intercept would be plenty. You guys see that? So if I plug 0 in here, I get 8 out. That tells me that these 2 points are on there, right? And so is 0, comma 8. You guys with me on that? And then I could draw my U shape through this. Another thing I could do is I could find the vertex. So where's the vertex?
3, comma.
Good. The vertex is over or maybe under 3. So how do you figure out what the point is that goes with 3?
You
Good. It's a point on the graph, right?
It's 2 below the x-axis.
So it's going to be 3, comma.
-2.
How do you know that?
Because if you go over by 2, it gets to 2.
Oh. Nah, I don't think you know that.
Can you just plug 3?
Yeah, good. It's a point on the graph, so it's an x, comma, f of x pair, right?
Oh, yeah, so
Or
like
p of x in this case. So take 3 and shove it in there. What do you get?
-1.
9 minus 18 plus 8,
Oh.
-1.
right? 3 squared minus 6 times 3 plus 8.
Close.
So that's what?
-1.
9 minus 18, negative 9 plus 8 is
Negative 1.
Okay, we're good at math, I promise.
Cool.
I don't know why that was.
So we found out it's at 3, comma, negative 1, and that's our vertex.
I said 1, I said -2.
Oh, and my picture's way off, right?
It's always off.
So that's at 3, comma, negative 1. So U shape, like so. Cool? Questions, Steels? What do you use a parabola for? Like, why am I having you do parabolas?
To get your television set.
They're really cool. Because they have this really neat property that if you drop something into them from infinity, it'll always bounce through the same spot.
Yeah, that spot's like equal distance to some.
So in here, there's a spot where if you consider kind of dropping something in here vertically, right? So you're beaming some kind of signal into this, and it bounces off the wall, it'll always end up at this thing. No, I just want you to know that point exists. That thing's called a focus. Yes, it is like a thing. We could find it, it would take some effort, and it's not the topic of
That's how
today.
satellites work, right?
Yeah, but this is exactly how satellite dishes work.
Yeah, well, that, yeah.
You guys see that?
See that.
Because what they do, right, is you want to be able to point this thing at some signal and concentrate that signal into one space. So that little reader thing, like the thing on the arm on the satellite dish, is sitting at the focus of that parabola. You guys see that? And so every signal that comes into that dish, all of it gets bounced in, concentrated right into the focus, and you can get higher gain on your signal.
Would it be different for a different kind of ray striking the hole?
So they all bounce off. You have to assume they all obey the kind of basic bouncing rules, which is that the angle at which it bounces off is equal to the angle at which it came in. That's maybe not necessarily in evidence here, because I don't really know what it means to bounce off of a curved surface, right? But you guys can all envision the tangent line there, and then think about it bouncing off the tangent line.
Triangles and
Yeah, and it's just a bunch of trig, so let's assume we can do it and not do it. Cool? What's the other thing parabolas do, other than satellite dishes? What else are these good for? What?
Plates.
Plays. No. I don't know, maybe. Not that I know of about that.
Maybe bridge arches? Arches in general?
That's also a good thought, but unfortunately is not quite right. Bridge arches are built using a slightly different shape. They're hyperbolic trig functions. How about falling objects? Falling objects are always trace parabolic curves. So if you go out and you throw a ball in the air, or if you go down to MJC, there's that cool ass fountain.
Yeah,
Have you guys seen the fountain?
No.
Oh, so if you happen to be down in Modesto, I really recommend that you go find this fountain. It's just a big pool that's got jets on the sides. And the jets they're basically a garden hose, right? They're just a little pump that takes a little bit of water and then shuts off. But what they end up doing is launching these like 3/4 inch diameter tubes of water. But they follow parabolic paths. So you can watch them trace the parabola. It's really fun.
yeah. Where I'm from in the mall, there's a section where there's just like it looks like 3 bricks like stood on end, but they have them like in a bunch of random places all over, and you can
Oh,
like,
and they
walk
kind of
underneath,
shoot.
and they'll shoot above you, and you can like look at everything,
Yeah.
and go across, and
It's very cool, right? When you just spray a garden hose in the air, the water makes a parabola. But these cool fountains just shut it on and off really fast, and so they get these little cylinders that fly through the air. It's pretty cool.
Singular streams.
Yeah, they're usually, the ones at MJC are about this long, so they're just barely long enough that you can see them start to bend.
That's cool.
guys know this pretty well.
Okay.
Isn't MJC